Good morning, everybody. Thank you, Jan, for this introduction. So first of all, I will start sharing my presentation, and then I will start. Should be this one. You let me know if you can see my screen.
We can see your screen. Thanks,
Okay.
Mr.
Thanks. So I will try to keep the camera open. I just mentioned to Jan that I have a bit of a problem with my connection. In case if I see that I keep receiving message of unstable connection, I will have to close my camera. Anyway, again, good morning, everybody, and thank you for this opportunity for presenting something, let's say, from my research or from my most recent research. Jan already introduced me, but I will do it kind again because, as you can see, the title of my presentation is on asphalt binder research, a Finnish perspective, while I'm actually a faculty in Italy and not in Finland, or at least not in Finland anymore. So I just want to give you a brief background of what I did and where I was working. So let's move to the next slide. Yeah, okay. So this is me, maybe with my short hair. And again, I'm a faculty at the University of Padua now. It's very recent. I moved there basically at the beginning of November last year. I'm still a visiting faculty at Aalto University. Before I was fully working at Aalto in Finland. That's why of the title of my presentation. I'm very much involved in RILEM, as Jan was anticipating. RILEM is the International Association of Academia, Industry, Researcher Institution working on materials, construction materials and structures. And then my studies were first in Italy, as I'm Italian, and then in the US for my graduate studies. As Jan was saying, I worked in several countries. I like to show this slide when I introduce myself, just to see, to show what I'm, where I was, at least visually, and also to give an idea that I have some academic diversity, which is not like changing topic. Research is really living and experiencing very many different countries and take responsibility in those countries in terms of the work you do and research, teaching, service. So I start from my very small hometown in Italy, then to Padua for my undergraduate studies, US, Minneapolis for my graduate studies, Germany for postdoc in Braunschweig, and then junior professor, a short period in Japan, then back to the US for a while, then Finland, at university, and now in Padua. And I decided to leave a question mark flag now in this slide because you never know what the future will bring, and if I will keep spinning around the world. I give a few information also on my affiliation, and my affiliation, I should say, for now. And I work at University of Padua, as I said. This is a 803 years old university. I think it's the fourth oldest university in the world. It's pretty large. University with 71,000 students, although I'm not even sure if the university knows how many students it really has, which a large majority of female students. This university is famous, especially because of the alumni that were here, alumni and also professors, include Galileo Galilei and Nicolaus Copernicus. And concerning the the organization is organized in 8 schools. I mentioned also about what is the offer that we have related to our field, which is experiment engineering. We have several classes all in English. And I reported this, this small reference to the motto of the department, and we compare it with what Alto identified as a motto, which is in our case is smart engineering infrastructures, which is where the direction of our school is going toward, which might be very different from other school. And this gives some idea of what is diversity in from academic perspective. So smart for Padua. While for Alto, what is the situation? Well, Alto is a small university, very small, relatively at least to larger university, which is Padua or might be other university in Europe. It was actually founded in 2010, so it's very recent, by merging 3 schools in the Helsinki metro area. It's organized in 6 schools. And the motto, the strategy of this school or this university is shaping a sustainable future. So you see from one side, you have a university focuses on smart technology, and the other more oriented towards sustainability. Okay, so this was to give you an idea that I work in one place and I'm still connected to my former affiliation, or it's still current in the sense that I'm visiting there, but it's officially my former affiliation. And that's why I'm presenting something from what I was doing as in Alto University. So I divide my presentation in 3 steps, as they are all part of one single project. The initial part is the phase 1, which I call the initial study, dates back a few years ago. And I will show you a bit of the evolution of one portion of this project that is still ongoing, actually. Hopefully will be completed by the end of the year. So what is the reason of this project? This project was originally starting as a request from the road authorities and some industrial partners. The point was that well, basically the Finnish market of binder is relatively small and very much traditionally oriented to the use of the same materials. And when some changes came, like in 2020, with the change in legislation, which was related to use of marine fuel oil from the International Marine Organization, there was basically a huge impact, especially in a country so small like Finland. When I say small, I mean small in terms of population. The population of Finland is a bit more than 5 million people. If you compare, for example, with, let's say, relatively larger country in Europe, we don't have actually a really larger country in Europe, but like Germany could be Germany, France, Italy, Spain. Well, then you can see that the big difference. And the impact was that this changed the market of the binder. This was a huge impact, as some of the products that were used to be used in Finland were not longer part of the options. And this also led to detrimental effects with changing refineries, closure of refineries, and new binder products, asphalt binder products, bitumen products came to the market, and they are actually unknown, or at least producer on asphalt mixtures, and the road authority itself were not really familiar with. There was really a big shake to the condition to the use of the binder for paving purposes in Finland. And this kind of sad because, as I said, it led to closure of refineries. And in this small country, you could see that industry that was like domestic one was basically disappearing, and some other I would say actors that are not domestic were coming to the market, but not necessarily with a purpose of innovation, but as an actor to sell their products. So the point was what to do when you don't know the product that you are coming to the market, and how you characterize something in a way that is fast enough. So either you have a payment that you want to repave because it needs maintenance, or it reached the end of the service life for the surface layer, or you want to design a new pavement, or you want simply to produce your asphalt mixture. When you have a product that you really don't know, you would like to have some tool that allow you to evaluate if that product, that binder, is good for the job or not, or if you can do something in case you can consider the binder for that job, but it's not exactly what you would expect. And the current way we characterize binder is relatively slow through rheology. It takes a few days because you have to go through aging, you have to go through, for example, dynamic rheometer testing, bending rheometer, and that takes the time that is not really the time that match the production. So you get the binder in there, and then you want to you produce asphalt mixture. So basically the method that we have are basically takes too much time. The idea, or actually the request from the road authority was to evaluate if there was a possibility to come up with a faster approach that could give us some information on the bitumen or the binder that was coming to the Finnish market. Since there was some agreement, I would say, in this, we decided to go for infrared tool, infrared spectroscopy, FTIR, for transform infrared spectroscopy. And since the test in itself is very rapid, and then try to get some information out of this basically through machine learning. This part is just one small part of the project that I'm talking about, and I will focus on this. And hopefully with such a test and a rapid analysis time, there could be the possibility of gain time to basically react in case we need to do some changes or add additives to the binder, adjust production, or simply say, no, the material is not exactly what we want for the job, and so reject the material. Okay, so I'm having again this message from the, I think I had to close the camera. I apologize for that. Okay, anyway, so what we did in the first step of this research was back like 4 years ago. We start to gather materials from the partner of the project, so binders from different sources and different providers. within the range of binder that, or list of penetration grades that were used in Finland. And we had a series of binder which were ranging from 5070 up to extender, and of just one single polymer modified binder. And the reason was that generally polymer modified binder is not used in the Finnish market, or very minimally. After that, we focused on performing FTIR tests. In parallel to all of this, what we showed today, we did the DSR test, but I will not really show any DSR result today. I will focus on the FTIR and the machine learning. We also perform oxidation, so basically we try to mimic the short-term aging of the binder, as you do that on RTFO. And then in the very beginning, what we did was to look at the quality of the data, or somewhat look at what the data were telling us, or trying to infer some conclusion result. And we did initially that with a simple principal component analysis. As if you know, a small note on the principal component analysis, and then I will come back also to this when we go into the second part of the presentation. This process it's a very simple. Well, some people say it's machine learning algorithm. Actually, it's not really that. It's a simple way to look at your data set and check on dimensionality and the meaningfulness of the data, assuming you can divide your data in some components, some blocks, I would say, to simplify, so that they bring some part of the information that they bring. This analysis is not a trained analysis. It's really a simple check of your data, try to analyze if they bring enough information and what part of the data or components are bringing information to you. As I said here in the slide, it doesn't really bring any meaning in the sense of real meaning or physical meaning. It's just a way to look at your data. And it's based on a linear combination of the variables. Some variables might bring more, might be more explanative. Some other might have less impact. The issue of this type of approach is that if you have very few data on for a specific case, then this analysis is actually blind. So it means that in our case, for example, if you have just very few data for a polymodified bitumen, it might be that this type of analysis is not able to capture that diversity in your data. And therefore, it's like I was saying in the slide that it's like you have an elephant in the room, but you cannot see that. Here are some basically, let's say, result or visualization of the data. I would say more than result based on the PCA analysis. We reduced the dimensionality of the data into dimension 2 because we have one principal component and a second principal component. And I will detail more about this in the second part of the presentation. And we try to look at the different samples here as divided by you see by the grade and also by year. You can identify some differences or some clustering. But still, if you look closely, you see that for example, the 160-200 seem to basically stay in a sort of cluster, but not for all the suppliers. So it's very hard to say that this PCA analysis is discriminating things. It's difficult also to say if there are there is an impact of source or binder, the batch, if there is a real consistent capability of discriminating things, at least considering all the data. This is the same plot, but from ordering the grading in a different way, not considering the providers. And you also see here that there is overlapping, there is significant overlapping across the binder grades, although some are really sticking out of the cluster. I already mentioned the problem of this PCA analysis, which is if you have few data about some specific material, in this case a specific binder, it's difficult to look at it's difficult to hope that this analysis might identify that, and it's actually not capable in this case. And I also was mentioning that this type of analysis is not like machine learning training analysis. It's just a simple evaluation of the data set. And also the fact that some differences, not only in the case of the polynomial-defined binder, in some cases the machine, I go back, this approach might think that the differences among binders is not there. So here I'm showing you some more plots in which we focused on fewer or like a subsample of the data. And here we could see differences across those subsamples, most likely due to difference in rheology, because that's what we noticed after comparing this data with the rheological data from dynamic environmental measurements. This for 7100 bitumen. This is from a 100-150, and we see here a clear difference between the two set of data. Might be depends on the source or the supplier. The supplier are different in this case. The origin of the binder is very difficult to say in this case. Also, here another example from another type of grading is 160-220. We see differences in years. Is very remarkable, but still within the same year of production, you can really see there are, for example, your tree clustering. And again, we don't know exactly what might be the reason. Producer might be the source, origin, batch. Is really hard to tell. Here, one more sample for basically an extender, and again, we can determine some difference, and but still there are some subclustering that are really difficult to tell what is the reason of this. Again, might be source or other condition. So what we decide to do next, as anticipated at the beginning of this initial part of the study, we decide to perform aging on the sample directly on the FTIR. And similarly to what you do on short-term aging with the rolling thin film oven test. So we short-term age the binder for basically 2 hours and at 163 degrees. And we took measurement on the FTR as the aging was progressing. I don't remember if it was every 4 minutes or something like that. And what we did, we obtained for you some subset of data was this kind of stripes still within the PCA analysis. But this kind of stripes, they were suggesting that potentially there is a way to somewhat discriminate binder from binder, as this is more informative than just one single point or average point from a measurement at a single aging condition. Despite of this, what we realize is that, the PCA analysis could have some potential, but in the end is so simple that it's not really giving us much information. So, for example, we are not able to say, okay, we have all this data, we have the PCA analysis, can we predict back the rheological properties of the binder? Which is in the end what we might want to reconnect when we decide the binder that we want to use for at the production level. So what was done next was to move into some modeling, which could be incorporated into the machine learning. In this case, it was real machine learning. And this is part of the second phase of the project. And in this case, we decided to use very simple models, a couple of simple models, still basing the approach on data analysis, on data set checking through the PCA analysis. So this is what we came up with. We reduced a bit amount of data that we used compared to all the sample that we had, and we tried to look at go somewhat with the same approach in terms of testing, so dynamic shear rheometer test, as to have a comparison of the result from the rheological analysis, and then the FTIR testing. And then use the entire data set into, we could say AI method or machine learning through two simple models that I will detail in a few slides. And then try to see if we can predict these rheological properties out of the chemical properties. I was saying before that I was going to come back to the PCA analysis very quickly, just to mention that the problem that we had, and we are still in the previous part of the presentation, the previous part of the study, was to obtain significant components out of the entire data set in a way that were meaningful for the next part of the analysis. And again, this is nothing else than reducing dimensionality from one system to another. Potentially, if you can even go from an n-dimensional system into a single or one-dimensional system, assuming that your data set allows that, which is not our case, but it's a good way to reduce the complexity of the problem. So here's just a sample representation of FTIR. Everybody, I guess, knows what are the different peaks and what they mean, and what is the what they refer to in terms of compared to the response, somewhat of the response of the binder. And out of this, we okay, what did I do? Yeah. We identified 12 significant peaks within those in the spectrum of the FTIR. And out of this, we noticed that again, similar to what we did in the first part of the research, again, the first everything could be reduced into two principal component, bringing together more or less 96% of the information out of the 12 features that were identified. So we're basically reducing the problem to a two-dimensional problem. I'm not going to detail all the peaks and their meaning because I'm sure you are very much familiar with that and what peaks are more related to, I don't know, to the saturates in the binder, or what is more connected to aging and so on. And next, what we did here is like a simple sample or a schematic. We look at the eigenvalue and cumulative variance that can be generated from the PCA analysis. Just to mention an eigenvalue, a larger eigenvalue might indicate that the principal component it represents as the largest contribution among the principal components. And yeah, just to here I can be more specific. It can be found that if you look at the original feature that are positively related with the distribution of PC1, so principal component 1, we have the vibration of CH and CH2 that are having the highest correlation, and the vibration of SO having basically the lowest correlation. And so you can do the same thing for the second principal component and see if they are negative or positive correlated to this principal component with respect to the features that you obtain from the FTIR spectra. Here is just a couple, the result of the two simple models that we used for machine learning. We went really the basis, the simplest that we could, because we were unfamiliar. It was like new to us. We went with a multiple linear regression model. We include frequency, temperature, peaks, and we try to predict phase angle and complex modulus. We had a total of 7,200 data after all the measurement and condition. And in this case, we split the data into 80% for training and 20% for testing. So to look at how, let's say, good our prediction were, and you can already see from the first plot that for the complex module they are not exactly good. We rely on the root on R square and on the root mean squared error to have a simple indication how valuable or effective was the model. But in some cases, as in this case for the multiple linear regression model, you can visually see that things are not really working. I would just want to make a note about the root mean square error, which has to be taken very carefully and cautiously, because it's affected by the scale of the original data. So, for example, what I mean, if you have a value, for example, the complex modulus that are in the high temperature, so where you have and low frequency, where you have smaller values, a variation in that range is really detrimental and might push up to your error and then worsen the root mean squared error. Anyway, if you look at this result from this multiple linear regression model, you see that for the complex modules, we're way far off from predicting anything meaningful. And even though in the case of the phase angle, we have some, I would say, decent parameters in terms of errors, well, the shape is not okay. It's definitely not okay. And I don't know if you took a statistics class, one of the first things that very first statistics class you take at university is the professor tell you that don't trust just the parameter, look at the shape of the plot. That's something that you should do as best. And as you can see, despite having nice numbers, it is really not providing a meaningful prediction. So the multiple linear regression model is not really what we want to consider, at least not in this case, although it might be something that you want to take as a benchmark, because depending also the amount of data, it might be that is capable of doing a better job. Here is the result with the second model, the Gaussian process regression. This model is doing a much better job. I don't say that it's doing a good job. I just say that it's much better than the previous one. We have good numbers in terms of errors for both cases, for complex modules and phase angles. So you might tend to say, yes, it's a good approach. In the reality, it is not really so good because you have quite a dispersion, in both cases, and so both for complex modules and phase angle. And you should be careful in what you do when using this simple approach. It's also to be noted that the Pareto frequency, looking at the contribution of the different features, the Pareto frequency is much smaller compared to temperature, and that is also what I was just mentioning one slide before. Be careful, high temperature measurement and low frequency. Where you have this kind of a strong variation in the measured data because you have small values, and this might be very detrimental when you use this kind of simple models. Okay, this is what we were at the end of the second phase of this work, and after that we were definitely not happy of what were our results. So we decided to move forward with basically with more models, a bit more, let's say, sophisticated, or at least more advanced. I don't know. You choose the word that you prefer, but let's say simply, I would say more models. And we moved into what I would call phase 3 of the study, which is the latest thing that we did, and there's actually a paper recently published on this. We took all the material that we could, and we are available for when we start this. So we have 79 asphalt samples, or types actually, and we have different 6 penetration grades. We also incorporate bio-based binders and 7 aging levels. And again, we relied on DSR and FTIR test. Concerning the aging level, we had for the short-term aging, we follow again the procedure of the RTFO and the similar condition for the PAV, single PAV, and then from that we increase the PAV duration to 40, 60, 80, and 100 hours, so that we could have several levels of aging. And the reason of this was also that connected to the fact that in Finland recycling is performed actually very often, and we could easily talk about multiple recycling, and also the window between one recycling cycle to another is relatively narrow. We're talking about 3 to 5 years. So we wanted to evaluate what could be the actual effect of multiple aging of the material from this perspective. The SR tests were run like in the phase 2 with 25, 4 millimeters from high to low temperatures. And yeah, this for the material testing. Concerning the model, we used 5 commonly machine learning models. We still kept the multiple linear regression as a benchmark, although we knew it was not the optimal model from the previous case. It's is in the end is one of the simplest approach. Another model we used was the support vector regression, which basically maps the input features into sort of high dimensional space, and then it identified the what is called like the optimal hyperplane, which is representing the data. And the good things of this model is that it can handle both linear and non-linear relationship between inputs and outputs, which allows to achieve higher accuracy and hopefully robustness when you have of your data set, maybe diverse data set or more complex or even simple data set. What else? Yes. I just okay, sorry. Then are we going to detail the next slide for the artificial neural network, the random forest, and then the extreme gradient boosting. And we also use a Bayesian optimization strategy to basically determine the hyperparameters and we maximize the performance of this model. Let me just a few words on the artificial neural network. I guess most of you are familiar with this. As you see from the picture, it's like consisting of an input layer and several in the hidden layer between the input and the output layer. The neurons are interconnected. Through weights, which determine basically how the different neural network layer influence each other. I report a simple the equation that you can associate to this model. Nothing more than that. For the random forest, it could be defined as sort of ensemble learning method, which is made of multiple decision tree that are constructed as you train this, and every tree is basically trained with a subset of data, random assigned subset of data, which somewhat is the strategy they try to use to reduce overfitting and somewhat also improve performance because they are computationally demanding. Due to this characteristic, basically, you try to reduce the model variance and again try to get less noise, improve the robustness of what you are going to predict. For the extreme gradient, is also like an ensemble learning method. Basically sequentially enhance each subsequent model using a gradient descent, and it's incorporates some sort of regularization techniques. Again, always to reduce any potential overfitting that you want to avoid. And then the Bayesian optimization. Well, okay, let me first say this. I talk about hyperparameters. When I talk about hyperparameters, I mean simply a parameter that try to control the learning process of a model, but is not a parameter learned by the model itself during the training. So it's sort of a tool. Let's say that is sort of a tool. So when we use this automatic hyperparameter optimization, is because while some of these models that I mentioned are somewhat powerful, the performance depends on selecting the appropriate parameters. So these tools helps to improve the performance. So to maximize the accuracy, we try to use this Bayesian optimization and determine the hyperparameter. Okay, I think I can stop with detailing this thing. So here I have some results. I start from commenting on this effect. I'm not going to give any visual on this. I will leave the visual comparison for the result of the models yeah. So if we look at the oil source, it was observed that from the FTR spectra, the sample are very similar. Is not surprising because we really didn't have polymodified bitumen. And this was confirmed also by the rheological properties. But yeah, so it's yeah, it's not much that I can say about the oil source effect. The functional groups were exhibiting some sensitivity to oil source, but limited, and the peak associated with the stretching in the SO was like showing some differences. The batch effect, also here we see a small, very small variation, low sensitivity to the production batches, also from the FTIR. In terms of penetration grade effect, the stretching vibration in the SO is around 1030 in the FTR spectra were the most sensitive to the penetration grade and suggesting that this part of the spectra vibration significantly influence the might significantly influence the rheological properties. With the aging, we could see that there were significant variation in the spectra, particularly again the SO stretching vibration, CO, and we also look at the weight values. I'm not reporting here, so that could are a bit more informative. So here we could see the weight, the distinct functional group could exceed 80%, so very significant. And then for the bioextender, the degree annual difference that between the sample I was observing in COC stretching vibration, and also here it was reflected into the weight values that we associate to the analysis. Anyway, let's go to the prediction model. That is what is well, more the core of this presentation. And we had in this case many more points than in the phase 2 of the study. So we were talking about 25 and almost 26,000 data points. We are still targeting complex modules and phase angle, but in this case, what we did was to reduce the amount of data that were assigned to the training from 80 to 70%, and we use 30% for testing. And we use for the hyperparameter optimization, we just use the Python. I think it was like scikit-learn in Python. So for I still on the Bayesian optimization, again, I would say it was employed for the hyperparameter selection of the model. And basically what happens is that optimizer is trying to search for the optimal parameter, for a combination of optimal parameter that minimize the coefficient of determination. And basically, if you look at the feature here, is like after 10, what is here? I never used this mouse, sorry. I was anyway, after 10 iteration, you could see that the objective function value converge along selection of the best hyperparameter combination. We also used to evaluate the performance of the machine learning model. We also used, together with R-square, so the coefficient determination, we used other parameters, again, the mean square error, the root mean square error, and the mean absolute error, and the mean absolute percentage error. The reason is that, okay, R-square is fine because it can give you a rule of thumb idea of what is going on. But as you get close to 1, then it doesn't tell you much more. And so you need to look at other parameters to discriminate between the quality and the performance of the models. And so that's why we use this other set of parameter, because, for example, the MSE, the RMC, and the MAE are more powerful. For example, the MSE represents the average square difference between real and predicted values, particularly, I would say, sensitive to outliers. RMC and MAE, can I say, measure absolute errors with the first one, the RMC, assigning greater weight to larger errors, and MAE, we treat basically the errors equally. And to account for possible relative differences, the percentage base error metric MAPE was also employed, and the combination of these things helped to give us a better idea of the performance of the models. So let's move to the result of the comparison of the models. Of the 5 models that we used. Here is for the complex modulus. I can tell again that the first model, which was the one that we use also in the second phase of the study, is performing the same way. So we have a poor prediction of the complex modulus, same result basically as in the other case. What we can see is also that the second and the third models achieve better performance, which might suggest stronger presence of nonlinear relationship between the features that we consider in the data that we have. So basically, in the asphalt binders chemical properties. And in case of the XGBoost model, this looks like to outperform all the other models. In terms of coefficient correlation R square, it achieves a very, very high value. And on top of it, it presented the lowest RMSE value, which provide the fact that it has a higher accuracy. Yeah, I will move to the next, and you can see here the XGBoost, which looks also visually the most consistent and accurate compared also to the other 4. Although the third and the fourth model are really doing still a decent job, I would say. This is the summary of the result for the phase angle for the same 5 models. Again, we see that yes, in the case of the linear regression model, we have a better prediction, but it's very spread out, and there is this kind of skewed form or shape of the data, which is really telling us that yeah, better numbers here in terms of R square, but RMSE, but not necessarily a good prediction. And while all the other 4 are doing much better job, even compared to the prediction of the complex modulus. There's well, if you look at the neural network and the 4th models, they show similar performance. And again, the 5th model, so the XGBoost, deliver the best result.
Teams oder kannst du eben per
Yeah. Excuse me, somebody has a microphone on. Can you please turn it off, please? Okay, Augusto, I think you've gone to mute. Augusto, I think you're still on mute.
Sorry.
That's okay. That's okay.
Yeah. Okay, can you hear me now? So I was saying that now I move to the final result slide, which is what we show here is trying to look at the different features and their contribution to a shapely additive explanation. This method is kind of trying to explain the prediction of a machine learning model based on a how can I say it's a game theoretic approach that is based on this classic shapely values, and each feature is basically regarded as a player, and you look at the player contribution to the final outcome. It's nothing else than that. It's very simple, very basic things. If you look at this for figures, plots, or I don't know, schematic, whatever you want to call. They display the feature importance based on the mean absolute sharp values, and then the straight impact on the outputs. And it is obvious that the top 5 most important features for predicting G-stars, the complex model phase angle, are temperature, frequency, and then surface size stretching, CH3 bending, and CC stretching. There is not really an exact order if you really want to be precise, but beyond these 5 features, the contribution of the other feature are, I would say, not insignificant, but relatively minor. So it means that the modules, the phase angle, are strongly correlating, influenced by the main 4 features, and those and parting this is the components is associated to the chemical properties. Okay. With this is my last slide of result. I have a simple conclusion, which is not really conclusion because the work is not completed here. The project is still going on. So far, I don't really, it's not really a conclusion, I'm sorry. But anyway, what we did was trying to combine experimental and machine learning approach to evaluate the asphalt binder in this changing market of Finland, which is very challenging for smaller country like Finland is. It might be not understood from perspective of a larger country in Europe, and at least that's what I learned by moving around different countries. What seems to be a small problem in a larger country it becomes a really severe issue in this kind of relatively smaller countries. So what we say is that initial results show some potential for the proposed method or methods. Let's say method in sense of like using FTR plus machine learning. The point is that also what we learned, and this was kind of confirming what is in literature, is that you need a large data set. The more data you have, the better. Of course, you need to check the quality, you need to check that it makes sense, the dimensionality with PCA. PCA is useful in that sense. And simple model doesn't mean simple is good. In this case, means that are not necessarily effective. And you could see from the 2 models that we used in the second part of this research. I also add a few more things since this work is somewhat also related to technical committee that I'm leading in RILEM. So I also had a few slides here so to make aware what is going on at international level and scientific community level. I'm leading a technical committee from RILEM on alternative material design and performance, together with my colleague from NCAP in the US, Fan Yin. we have 3 groups. Okay, so our objective is to work on alternate payment materials, try to continue the work from the previous TC, which was on waste and secondary materials, and try to turn this use of these alternate payment materials into something that is native in the design of road composite or paving composites. There are 3 TG leaders from KTH, from NTPE, and from IT in the Institute of Technology in India, so Maria Chiara, Salvatore, and Krishna. And last, I guess, is to advertise the conference or ISBM from running ISBM that will take place in Padua in 2026. And call for paper will be open very soon. With this, I want to thank you, all the partners of the project, Moribit project from Finland, Road Authority, industrial partners, all the research teams that was there when I arrived in Alto, and some left in the meanwhile. I left too, some are still there. And thank you for this opportunity to presenting this work. And yeah, again, thank you very much for listening.